Hello everyone. So far, we have seen the general nature of linear programming problem. We have seen how linear programming problems are used to solve varieties of OR applications. We have seen the implementation of graphical method to solve LP problems wherein we had the total number of decision variables equal to 2. And wherever the number of decision variables exceeded 2, we have made use of simplex algorithm to solve such type of LPP. In this simplex method, we have seen the usage of slack variables, surplus variables, and artificial variables, of course, depending upon the type of the inequality constraints that we were dealing with. Now, apart from solving the problems using simplex method, we have also seen another variation of LP problem called as assignment problem. It was also stated that the simplex algorithm could be used to solve any LP problem for which the solution exists. However, as the number of variables and constraints increase, the computation by this method becomes more and more laborious. Therefore, wherever possible, we try to simplify the calculations. One such model requiring simplified calculations is termed as distribution model, or it is also called as transportation model. It deals with the transportation of a product available at several sources to a number of destinations. The name transportation model is, however, misleading. This particular model can be used for a wide variety of situations such as scheduling, production investment, plant locations, inventory control, employment scheduling, personal assignment, product mix problems, and many other, so that the model is really not confined to transportation or distribution only. With this small background, let me tell you the coverage of this particular model called as transportation model. I'll just give you a brief introduction followed by a mathematical formulation, and then we move on to find out the initial basic feasible solution for the transportation problems. Any transportation problem, if you want to make an attempt to solve it, the first step is you need to find out the IBFS. Without IBFS, you cannot go to the next step, what is called as moving towards optimality. And then we will see how unbalanced transportation problem works and degeneracy, that is degenerate transportation problems, when degeneracy occurs in case of transportation problems. Now, as far as, let us see what exactly is the transportation model. The transportation problem is actually a special type of linear programming problem where the objective is to minimize the cost of distributing a product from a number of sources or origins to a number of destinations. Because of its special structure, the usual simplex method is not suitable for solving the transportation problems. Let us look at the introduction of this. The origin of transportation problems dates back in 1941 when Heffel Hitchcock presented a study entitled The Distribution of Product from Several Sources to Numerous Localities. Now, this particular presentation of Hitchcock is considered to be the most and the first important contribution to the solution of transportation problems. However, in 1947, T.C. Koopmans presented an independent study not related to Hitchcock problem, but his presentation was titled as Optimum Utilization of the Transportation Systems. Let me tell you one thing, these two contributions are mainly responsible for the development of transportation models which involve a number of shipping sources and a number of destinations. Each shipping source has a certain capacity and each destination has a certain requirement associated with certain cost of shipping from source and destination. The objective is to minimize the cost of transportation while meeting the requirements at the destination. The transportation problems may also involve movement of product from plants to warehouses, warehouses to wholesalers, wholesalers to retailers, and retailers to customers. Now, with this sort of a background and introduction, let us move further and try to understand what exactly the definition of a transportation problem is all about. You would have seen these terminologies in my introduction part also. The transportation problems deals with the transportation of the product manufactured at different plants or factories, which we call it as origins, to a number of different warehouses, we call it as destination. So the whole idea is to transfer the product from source to destination. That's what I have said. The objective is to satisfy the destination requirements within plant's capacity constraints at minimum transportation cost. Now, having known the definition of this, let us try to understand with a simple diagram how the transportation problem works. As you see in front of your screen, I have three factories which I have denoted on the left hand side, and I have three warehouses on the right hand side. Factories are denoted as F1, F2, F3, and warehouses are denoted as W1, W2, W3. And you see a couple of arrow marks connecting each of these factories to each of these warehouses. If you try to recollect, what we have done in assignment problem was, the assignment problem actually works on one-on-one basis. That is 1:1 basis. One of the example we discussed in the class was assigning the subjects to the teachers. And we said that at the end of the day, one subject was taught by one teacher. We have never come across one subject taught by a couple of teachers, or probably couple of couple of subjects taught by couple of teachers, or anything such like that. The whole idea in transportation problem is you will not have 1:1 ratio. That means factory 1 will not be supplying the products to warehouse 1. You are not going to ship the products from factory 1 only to warehouse 1, right? In case of transportation problem, what happens is any number of products can be shipped from any factory to any warehouse, right? I repeat, any number of products can be shipped from any factory to any warehouse. Of course, you have to keep in mind the supply and the demand, right? Now, when you look at the three arrows that is coming out of F1 and is going to three warehouses W1, W2, W3, that is what it means, that factory 1 can supply the products to warehouse 1, it can supply the products to warehouse 2, it can also supply the products to warehouse 3, and similarly factory 2 and factory 3. Now, let us look at what is this supply and demand all about. On the left hand side, you have supply, which is called as S1, S2, S3, and on the right hand side, you have a demand called as D1, D2, D3. Now let us understand what is the significance of this supply and demand. Factory F1 can supply S1 products. That means the total number of products supplied by factory F1 will be S1. Similarly, the total number of products supplied by factory F2 will be S2 and factory F3 will be S3. That means the three factories will supply a total of S1 plus S2 plus S3 products. Now focus on the right hand side. We have three warehouses and the demand at each of these warehouses is D1, D2 and D3. That means the demand at warehouse 1 is D1, the demand at warehouse 2 is D2, the demand at warehouse 3 is D3. Now put together, what does the structure of this transportation problem tells us? It tells us like this, that the total number of products that can be shipped from factory 1 is S1. These S1 products can go to warehouse 1, can go to warehouse 2, can go to warehouse 3. That means factory 1 has got limitation of supplying S1 products. That's all. It can supply to any of the warehouses. It does not matter. On the other hand, when you look at the warehouse 1 demand is D1, right? Now, warehouse 1 can take the products from factory 1, it can take the product from factory 2, it can take the product from factory 3. At any given point of time, warehouse 1 can take the products from any of the factories, that does not matter, but the total demand should be D1, right? So the total supply is S1 plus S2 plus S3 and the total demand is D1 plus D2 plus D3. When the total supply is equal to the total demand, the such type of transportation problem is called as balanced transportation problem. I repeat, when total supply is equal to the total demand, the transportation problem is termed as balanced transportation problem. Now let us look at the general structure of the transportation problem. I have the factories on the left hand side, F1, F2 up to Fm, and then I have the warehouses, and then I have the supply availability and the demand at the bottom, right? So if you look at this, the factory F1 can supply S1 products, factory F2 can supply S2 products. Similarly, Fm factory can supply Sm products, that is availability. At the same time, the demand at different warehouses. W1, the demand is D1, which is there in the red color at the bottom. W2, the demand is D2, and so on. Now, this particular matrix, what is written inside, is called as cost matrix. You have the cost written in terminologies used as C11, C12, C21, C22, and so on. So what does it mean is, if you look at C11, which is there in the cell F1 and W1, am I right? C11 is in the first row, first column, that is intersection of F1 and W1. So C11 means it is the cost involved in transporting one product from factory 1 to warehouse 1. I repeat, the significance of C11 in this matrix is it is the cost involved in shipping one product from factory 1 to warehouse 1. Similarly, the cost involved in shipping one product from factory 1 to warehouse 2 is C12. C21 means cost involved in shipping one product from factory 2 to warehouse 1, right? Similarly, all other cost involved in this particular matrix. Okay. Now, this is the mathematical formulation of the transportation problem. I don't think I need to explain you all these things. It is assumed that the total supply is equal to total demand. And the objective is to find out the minimum cost, right? That is, minimize the total cost of transportation, that is Z is equal to summation of I is equal to 1 to M, summation of J is equal to 1 to N, Xij, Cij. So this is the objective function. But of course, the minimization should satisfy two important constraints, and they are called as availability constraint, and the another one is called as the requirement constraint, right? That is why we say total supply should be equal to total demand. Now, having this, let us proceed with the assumptions in transportation problems. There are a couple of assumptions in transportation problems. The first one is the total quantity of item available at different sources is equal to total requirement at different destinations. Item can be transported conveniently from all sources to destinations. Unit transportation cost of item from all sources and destination is certainly and precisely known. The fourth assumption, transportation cost on a given route is directly proportional to the number of units shipped on that particular route. And the last assumption in transportation problem is Absolutely no doubt. The objective is to minimize the overall transportation cost. Let us look at the definition part, right? The first definition is feasible solution. A set of non-negative individual allocations x of ij greater or equal to 0 is called as feasible solutions. We will come across these terminologies as and when we proceed in solving the problems. The next terminology is called as basic feasible solutions. What it says, a solution to m number and n destinations is said to be basic if number of positive allocations are m plus n minus 1. That is called as non-degenerate basic feasible solutions. We will see this again. And the last terminology is called as optimal solution. Now, before that, we have seen that in case of basic feasible solution, if the number of positive allocations are m plus n minus 1, it is called as non-degenerate basic feasible solution. However, if it is less than m plus n minus 1, it is termed as degenerate basic feasible solution. We will see the difference between both this degenerate and non-degenerate as we proceed in solving the problems. And the last definition is the optimal solution. Of course, the crux of the entire operation research world is optimality. A feasible solution is said to be optimal if it minimizes the transportation cost.